Assalamu alaikum. Hi students, today is our lecture number 21 for classical mechanics. We are studying chapter number 4 of calculus of variation for classical mechanics. That is the course of BS semester 5th, and the course code of your subject is PHY 509. Previously we discussed about what is Hamilton's calculus of variation. Now we are going to move further. We discussed three definitions for the calculus of variation. Now we're going to move to the next point, that is in which we're going to start from the contents. We're going to discuss about the applications of techniques of calculus of variation. There is first example that is previously continued. We discussed about the shortest distance between the points, and the other is the second example, and in the last we have references. Now moving to the next point. As we are discussing about the applications of techniques of calculus of variation, in this we are going to continue with the first example. The last work we did was the value of C1, that was y dot over 1 plus y dot is equal to C1. We squared the both terms on the right hand side and the left hand side, and rearranging we got C1 square is equal to y dot square over 1 plus y dot square. Then y dot square is equal to C1 square bracket 1 plus y dot square bracket close. Y dot square is equal to C1 square plus, we have multiplied C1 square inside, so we got C1 square plus C1 square into y dot square. Now we're going to take the term C plus C1 square y dot square to the left hand side, that will become minus sign. Then y dot square will be taken common, and then y dot square bracket 1 minus C1 square is inside the bracket is equal to C1 square. Then y dot square, taking that term in the division, so we got C1 square divided by 1 minus C1 square. So to remove that square, we'll take the under root on both sides, so that will become here the under root and the square will be cancelled, so here will become y dot is equal to under root C1 square divided by 1 minus C1 square. Now taking this value under root C1 square over 1 minus C1 square equal to a constant C1 C2, then y dot is equal to C2, giving that equation number 8. As we know that y dot is a single differential, and because of the x variable, so we have dy over dx, that is the Euler equations. Dy over dx is equal to C2, taking the dx from the denominator to the right hand side and integrating, we get integral dy is equal to integral c2 dx. Now after integrating that value, we will get y is equal to c2x plus c3 is the integration constant, giving that equation number 9, which is an equation of straight line. Thus the points P1 and P2 will all be on the straight line. So we can write y1 is equal to c2 x1 plus c3. They are the 2 points on the straight line 1 and 2. So we are going to try 2 line equations. Second point will be y2 is equal to c2 x2 plus c3, and giving that equation, first equation of y1 giving equation A and y2 giving equation number small b. Subtracting these equation, we get, as you know that when we have to subtract these two equations, we have to change the sign. So y2 is equal to c2 x2 plus c3 minus y1 is equal to plus minus, plus sign is converted into minus c2 x1, here plus sign is converted into minus c3, then the terms will become y2 minus y1. Here c3 will be cancelled, only c2 will be taken common here, and inside the bracket will be x2 minus x1. So giving that equation number C. From here we took the x2 minus x1 term in the multiplication to the left hand side in the denominator. We got y2 minus y1 over x2 minus x1 is equal to c2. Now considering the equation 1, we have L is equal to integral x1 to x2 bracket 1 plus y dot square whole power 1 by 2 dx. Then L is equal to integral x1 to x2. As you know, y dot was equal to c2, so we wrote here c2. That will become 1 plus c2 square whole power 1 by 2 dx. As that is a constant, so it can be taken out of the integral. So that will be written as L is equal to bracket 1 plus c2 square bracket 1 by 2 and integral x1 to x2 dx, and L is equal to 1 plus c2 square whole power 1 by 2 into x2 minus x1. So from here we get from the previous equation we get that c2 is equal to y2 minus y1 over x2 minus x1. So substituting the value of c2 here, y2 minus y1 over x2 minus x1, putting here, we get L is equal to bracket 1 plus bracket y2 minus y1 over x2 minus x1 square bracket 1 by 2 into x2 minus x1, taking the, opening the squares, separating the squares, that will become y2 minus y1 whole square divided by x2 minus x1 whole square, and then taking the LCM, so we have L is equal to bracket x2 minus x1 whole square, and taking the LCM, that here is not the term, so 1 multiplied by x2 minus x1 will give x2 minus x1 whole square plus x2 minus x1 whole square is multiplied by 1, that is 1 plus y2 minus y1 whole square and whole power 1 by 2, and that is x2 minus x1 and multiplied by x2 minus x1. Now we cancel, when then we separate the power 1 by 2 above and below, so we get x2 minus x1 only in the denominator, as 2 and power 1 by 2 are cancelled here. So L is equal to bracket x2 minus x1 whole square plus y2 minus y1 whole square have a whole power of 1 by 2 divided by x2 minus x1 multiplied by x2 minus x1 are cancelled here. So that will give us L is equal to bracket x2 minus x1 whole square plus y2 minus y1 whole square whole power 1 by 2.
So, what is the shortest path between 2 points? And you say, oh, it's easy. This is an easy question. No, it's not easy. It may seem obvious in a flat plane, but it's not obvious in a non-flat plane. But we're going to do it in a flat plane in 2 dimensions, just because that's the first place to start. So here I have point x1, y1. I want to get to point x2, y2 in the shortest with the path. And this is the thing. It's a variational problem, but we're not trying to vary one value. We're trying to vary a function. We're trying to vary the function that is this line. So that makes it much more complicated. And this is our first step into the calculus of variations. So in general, we have this. If I have some integral like this, so j could be anything. I'm just calling it j because, I don't know, j is kind of cool. And I have some function, and I want to find the function that minimizes the integral. I don't want to minimize the function. I want to find this function such that this integral is minimized. And that's what we're doing here, right? Because I want to integrate along this path and find the distance. And I want to find what function minimizes that integration. It turns out that the solution's not trivial, but super, super, super useful and very important. And it's so useful, I'm going to do it in purple. This is the Euler-Lagrange equation. I'm not going to drive it. Okay, but we need to use this to solve this problem. And it turns out that we can use this for a whole bunch of mechanics problems. So this says that if I have a function of x, y, and y prime, and y prime, just to be clear, y prime is dy dx. I mean, and I'm using the variables x and y, but we could use x and t, or whatever. It doesn't matter. And that's what's great about this. It doesn't matter what your variables are. But I need this integral depends on the x function, the y, the value of x, it could depend on y, and the derivative of y. Then the function that minimizes this has to satisfy this equation that says the partial of f with respect to y minus the derivative. Remember, these are partials, not derivatives, and that's an actual derivative. The derivative with respect to x of the partial of f with respect to y prime is equal to 0. So let's do it. How do you do this to show that the path between 2 points is a straight line? So let's pick a little piece right here. What I'm going to do is say, what's the path length? I'm going to say L equals the integral from, I'm just going to call this 1 to 2 of ds, where ds is the sum of the little pieces along that function. So in Cartesian coordinates, x, y in 2 dimensions, then ds is going to be, you can imagine this, right? There's my little path piece. This is dx, that's dy, that's a y. So that would be the hypotenuse. So it'd be the square root of dx squared plus dy squared. And that's my function I'm going to put in there. But I can't do that, right? Because I don't have it in this form. Right? I have a dx and I have a dy. I just want dx. So let's write this as ds equals the square root of 1 plus dy dy dx squared. Well, I don't know what I'm doing here. Dx. I had a trick. I factored out the dx, right? Because this is, I divide everything by dx squared. Yeah, that's right. So then I have, I want to say this is, yeah. That's going to be, this is dy dx squared, right? I should have left it that way. So it's equal to the square root of 1 plus, this is going to be dy dx, quantity squared. It's not the second derivative. It's a quantity squared. So this is actually y prime squared. Now I don't have the dy in there, right? I don't have to worry about that. I have it in this form. So that's my f. So I can now do my partial derivative. So the first thing I'm going to do is take the partial derivative of this with respect to y. That's pretty easy. The partial of f with respect to y is equal to 0. Why? Well, there's no y in there, right? And it's a partial derivative, so it doesn't really matter. That's easy. Now I can take the partial of f with respect to y prime. So I'm going to write this as, actually, this is not f. F is just the square root part. So I'm going to write it as 1 plus y prime squared to the 1/2, because I like to think of things that way. So if I take the partial of that with respect to y prime, I can use the chain rule. It's going to be the derivative of this, which is 1/2 times 1 plus y prime squared to the negative 1/2. Right? I have to decrease that by a power of 1. Now I have to take the derivative of the stuff inside. The derivative of 1 is 0. The derivative of y, the partial, with y prime squared is going to be 2y prime. And the 2's cancel. So now I need to find dx, I could, of the partial of f with respect to y prime. I could do that, right? And I would have to take the derivative of all these terms, but I'm not going to. Because I know this is, since this is 0, this is 0. The derivative of f with respect to y prime is 0, which means the partial of f with respect to y prime is a constant. Right? If I take the derivative and I get 0, then this part right here has to be a constant. Okay, so let me move to my next page, and I will say this. Here's my function. Partial of f with respect to y prime, it's going to be this stuff. I'm going to write it as y prime divided by the square root of 1 plus y prime squared equals c, some constant. So let's just multiply both sides by this to get rid of the fraction, and I get y prime equals c, the square root of 1 plus y prime squared. Now I'm going to square both sides, and I get y prime squared equals c squared, but I mean, you could just call it c if you want. A lot of people do that. I'm not going to do that. I'm going to write it as c squared because I care about you guys. Times 1 plus y prime squared. Now let's multiply this out, and I get y prime squared equals c squared plus c squared y prime squared. Now I'm going to subtract this from both sides. It doesn't really matter. I'm going to say y prime squared minus c squared y prime squared. And I'm doing way more work than I need to. You could stop earlier, but equals c squared. And then I'm going to factor out the y prime, and I get y prime squared times 1 minus c squared equals c squared. And now I get y. Now I'm going to divide both sides by this. Y prime squared equals c squared over 1 minus c squared. And then I take the square root. Y prime equals a constant. I'm going to call it k. So this is my solution right there. I want a function f such that the slope is constant. That's what that says. This says dy dx equals some constant. Well, then what's y and what's x? Well, now I'm actually done, because if the slope is constant, I can use this. Y equals some constant. I'll call it now m. Actually, I should have called that m. That would have been funny. M x plus b, right? And I can get that by integrating both sides. I can actually, let's do that. So let's say dy equals m dx. I integrate both sides, and I get y equals mx from x1 to x2. So that's going to be m, and this is from y1 to y2. So I get y2 minus y1 equals m x2 minus x1. And that's my function, which is a line. The end. So, I mean, I think it's confusing sometimes to see this, because you kind of have to do two things that I don't really like. One used this Euler-Lagrange formula, but I didn't show where that came from. I don't really want to derive it right now. And number two is this getting this y prime squared, this y prime in there, getting rid of the dy, and instead getting a y prime. That's the other trick. You need a function of x, y, and y prime. Okay. So we'll do another problem, but there's your first introduction to the Euler-Lagrange equation.
That equation in the last you can see gives the minimum distance between the 2 points P1 and P2, that are the examples or applications of the calculus variation. Now moving to the next point and example 2. A particle of mass m is projected from origin O with an initial velocity v m projected from the region O, initial velocity v, making an angle alpha with the horizontal. Find the Lagrangian L and determine the path of the particle from the time t is equal to 0 to some other point t such that I is equal to integral t to is equal to 0 to t L dt is minimum. That is also the Euler's equation. Here we have two coordinates x and y. We have a parabolic path of the particle. The particle is projected from the point O origin having mass m, and after projecting it moves with the velocity v and makes a parabolic path and strikes with the ground after some time t, and that velocity that point at certain height has a location or position pxy, and the angle is alpha. Resolving the components of velocity v, we have Ax is equal to v cos alpha and vertical component Vy is equal to V sin alpha. Let at any instant t, the position is given by Pxy. At this point, the kinetic energy will be T is equal to 1 by 2 mx dot square plus 1 by 2 my dot square, because both components are involved of the coordinates x and y. Now the potential energy is given as V is equal to mgy. So the Lagrangian is L is equal to T minus y. We have studied that previously. So putting the value of T and V, in that equation, so L is equal to 1 by 2 mx dot square plus 1 by 2 my dot square minus mgy. As integral I is equal to, at integral t is equal to 0 to t, substituting the value of L, 1 by 2 mx dot square plus 1 by 2 my dot square minus mg y dt. Now comparing the integral with the general integral, that is I is equal to integral t is equal to 0 to t f of x y dot, here y is minimum, so f of x y dot will that equation is compared with the above equation. So we have f of x y dot is equal to 1 by 2 mx dot square plus 1 by 2 my dot square minus mgy. In this case time t is independent variable and x y are depend upon the time t. By calculus of variation, if the following conditions are satisfied, number one is d by dt partial into partial f over partial x dot in minus partial f over partial x is equal to 0, and the other is d by dt into partial f over partial y dot minus partial f over partial y is equal to 0, giving that equation, first equation equation number 1 and the second equation equation number 2. Comparing the two equations, first and previous equation, that is partial f over partial x dot is equal to partial over partial y 1 by 2 mx dot square, that will give 2 by 2 mx dot square. 2 by 2 is cancelled, so we are left with mx dot, and partial f over partial x is 0. So substituting that value in first equation, so we have d by dt into mx dot is equal to mx dot minus 0 is equal to 0, d by dt mx dot is equal to 0. Then integrating that equation, we get mx dot is equal to constant and x dot is equal to constant over m, and then we have x dot is equal to c1. Now by applying the boundary conditions, initial boundary conditions, we have t is equal to 0. So from above equation, x is equal to v cos alpha. So substituting that value in that equation, we get c1 is equal to v cos alpha. Hence x dot is equal to v cos alpha. Here x dot is equal to dx by dt, that is equal to v cos alpha. From here dt is taken to the right hand side, so that will become dx is equal to v cos alpha dt. Integrating both sides, we get integral dx is equal to integral v cos alpha dt, and that gives x is equal to v cos alpha t plus c2. Now t is equal to 0 gives x is equal to 0, so substituting that value, we get 0 is equal to 0 plus c2, then c2 is equal to 0. Substituting in the previous equation, x is equal to v cos alpha t, c2 we get 0 here, so x is equal to v cos alpha t plus 0, and x is equal to v cos alpha t, that gives equation number 3. Now considering equation number 2, partial f over partial y dot is equal to my dot, partial f over partial y is equal to minus mg. From equation 2, we got the value of partial f over partial y dot, that is my dot, and partial over partial y is equal to minus mg. Then substituting that values in the equation 2, we get d by dt my dot plus mg is equal to 0. So d by dt my dot plus mg is equal to 0. That gives my double dot, as y dot is differentiable with respect to t, so we get my double dot plus mg is equal to 0, taking the mass constant out of the bracket. So m into y double dot plus g is equal to 0. As we know that mass cannot be 0, so the coefficient of m is equal to 0. So y double dot plus g is equal to 0 gives y double dot is equal to minus g. As we know that y double dot is equal to dy dot over dt, so that will come dy dot over dt is equal to minus g. Now integrating that equation, we get y dot is equal to minus gt plus c3. c3 is a constant. Now to find the value of c3, we have the initial conditions. we put z is equal to 0 and y dot is equal to v sin alpha. So v sin alpha is equal to 0 plus c3. So c3 is equal to v cos sin alpha, and substituting that value in the previous equation in the place of c3 we get y3 is equal to minus gt plus v sin alpha. So again y dot is equal to dy over dt. So substituting that value dy over dt minus gt plus v sin alpha and integrating it, taking dt on the right hand side, we get y is equal to gt square with respect to t, gt square minus gt square over 2 plus v sin alpha plus c4. Now again applying the initial conditions, t is equal to 0 and y is equal to 0. When time is 0, the height y is equal to 0. So substituting 0 here, we got c4 is and 0 here we got c 0 c4 plus 0 plus 0 is equal to 0. Hence y is equal to minus gt square over 2 plus v sin alpha t plus 0. Y is equal to minus gt square by 2 plus v sin alpha t gives equation number 4. From here we get, from previous equation we get x is equal to v cos alpha into t. So from there t gives is equal to x over v cos alpha, substituting that value here. So we get y is equal to minus into g into x over v cos alpha whole power square divided by 2 plus v sin alpha. So from here that becomes y is equal to minus g by 2 into x square over v cos square alpha plus v sin alpha dot x over v cos alpha. Cancelling v with v, we get y is equal to x tan alpha plus minus gx square over 2v square cos square alpha. This is the equation of parabola. Thus the particle will have a parabolic path. That is the solution of the mass m moving from the point origin O in the two coordinate system xy and attaining a parabolic path and then striking to the ground.
Assalamu alaikum. We are studying various applications of Lagrange equation of motion. So in today's lecture we will study projectile motion. We will find out equation of motion for trajectory of projectile through Lagrange equation of motion. So what is projectile motion? It is a form of motion experienced by an object or particle that is projected near Earth's surface and moves along curved path under the action of gravity. So we will consider a particle of mass m which is projected from the origin of coordinate system x, y with certain initial velocity u at certain angle, let's say alpha. So this is projected, it would follow a curved path under the action of gravity. It will gains maximum height and then will move downward. So a particle of mass m is showing this trajectory under projectile motion at a certain instant of time. Let's say its velocity is u. We can find out velocity components at any point during its motion. Let's say at this point the components of velocity are ux, uy, making certain angle theta or alpha. this component ux will be u cos of alpha, uy will be u sine of alpha. So we can see the horizontal component of velocity will remain same during the whole motion while its vertical component is changing. Let's say at this point we can find the velocity components. It will be ux, it will be uy. So at this point vertical component of velocity will be 0 and ux again will be u cos of alpha. Similarly, at any point when it will move downward, at this point the components of velocity will be ux again same in the same direction and uy will be vertically downward, so it will be minus u sine of alpha due to its direction. So it is a two-dimensional motion. There are only 2 degrees of freedom, 2 independent coordinates. Now we need to find out Lagrangian of this system in order to find trajectory of particle, trajectory of projectile motion through Lagrange equation of motion. So we need to know the total kinetic energy, total potential energy of this system to find out Lagrangian T minus V. So we can write total kinetic energy, that will be half mx dot square, velocity, x component of velocity and y component of velocity, that will be y dot square, and potential energy for the system will be depending on vertical component y, depending on height gained by projectile motion. Then the Lagrangian simply will be half m x dot square plus y dot square minus mgy. So from the form of Lagrangian we can see there are 2 generalized coordinates x and y. So there will be 2 equations of motion for x and y, which are d by dt partial L over partial x dot minus partial L over partial x equals to 0, and the second equation will be d by dt partial L over partial y dot minus partial L over partial y equals to 0. So next we will find out these derivatives to solve equation 2 and 3. Partial L over partial x dot, partial L over partial y dot, similarly partial L over partial x and partial L over partial y from equation A, from Lagrangian of system. So we can see partial L over partial x dot will be mx dot, and partial L over partial x from this will be 0, no x component. Similarly partial L over partial y dot will be only due to second term, that will be my dot, and partial L over partial y will be minus mg. So writing these derivatives, partial L over partial x dot, which will be mx dot, partial L over partial x will be 0. Similarly partial L over partial y dot will be my dot, partial L over partial y will be minus mg. Now substituting values in equation 2 for x components and for y components in equation 3. So solving equation 2 first, d by dt of partial L over partial x dot is mx dot minus 0. So from here taking its time derivative, the equation will be mx double dot equals to 0. Mx double dot equals to 0. And now solving equation 3, d by dt of partial L over partial y dot is my dot minus plus mg equals to 0. Taking its time derivative, it will be my double dot plus mg equals to 0. So now we will further simplify these two equations to find out trajectory of projectile motion. So solving equation 4 first, mx double dot equals to 0. Mx double dot equals to 0 or x double dot equals to 0. We can integrate this equation. Integrating this equation, x dot will be equals to constant of integration. Let's say it is a. A is the constant of integration. So x dot which is vx, ux, x component of velocity. So x dot is ux, x component of velocity. It is a is constant. It means the horizontal component of velocity is constant, and ux equals to u cos of alpha. It means the value of this constant of integration will be u cos of alpha. So we can integrate this equation a, x dot equals to u cos of alpha to find out x. So integrating this equation, it will be x. Integration is over time, it is dx over dt equals to u cos of alpha. Then from this, dx equals to u cos of alpha into dt. So after integration, x will be equals to u cos of alpha into t plus another constant of integration. Let's say it is b. So we can find out this constant of integration at t equals to 0. At initial point, displacement is 0. So x will be equals to u cos of alpha into t. Now we will find the value of y from equation 5. From equation 5, my double dot plus mg equals to 0. My double dot plus mg equals to 0. So y double dot plus g equals to 0. Y double dot equals to minus g. We will also integrate this equation twice to find the value of y. So integrating once, it will be, it is d2y over dt square equals to minus g. So integrating once, we will get dy over dt equals to minus g minus gt plus c. C is constant of integration. So we can find the value of c at some initial conditions at t equals to 0. At t equals to 0, t equals to 0, we have this y dot dy over dt is y dot will be equals to c. Y dot is vertical component of velocity, which is uy c. So the value of this constant of integration is u sine of alpha. So substituting back in this equation the value of c, it will be dy over dt, which is y dot, equals to minus gt plus u sine of alpha. Now we will integrate this equation again to find the value of y. Integral of this derivative will be y equals to minus g. Integral of t will be t square by 2 plus u sine alpha. Integral of dt will be t. Again adding another constant of integration d. The value of d can be calculated at t equals to 0. At t equals to 0 we have y equals to 0. So the value of d will be 0. And y will be u sine alpha t minus half gt square. This will be vertical displacement. Now we can couple these two equations to find out equation of trajectory of projectile. So we can see, we can substitute the value of t from equation 6 in equation 7 to eliminate the value of time. So from here the value of t will be x over u cos of alpha. We can substitute here y equals to u sine alpha and t is x over u cos of alpha minus half gt square will be x square over u square cos square alpha. So we can combine these functions. Sine alpha over cos alpha will be tangent alpha. So after combining these values, y will be equals to u. U will be cancelled out. X sine alpha over cos alpha will be tangent alpha. So it will be x tangent alpha minus will be g x square over 2u square cos square alpha. So this is the equation of trajectory of a particle. That is calculated through Lagrange equation of motion.
Today's lecture is still here. Next will be our lecture continued. Thank you so much. Allah Hafiz. These are some of the references you can follow for the classical mechanics and the lecture we are studying. If there is any difficulty, you can get a reference from here and help. You can ask me your question. If there is any difficulty, we can revise the topic. If there is any kind of difficulty, you can solve the problems regarding the Euler's equation and use them as a sample. Use that lecture as a sample for the solving the problems of Lagrange Euler's equation from the calculus of variation. Thank you so much. Allah Hafiz.